which will be given by Ken Designer. Again, I think it's not that necessary to introduce her because, as a matter of fact, Barbara introduced her in her talk as for the topics which they have in common. And so welcome. I'm very happy that you are here, and we are looking forward to hear something how people can teach robots. So, please.
Thank you. No? Well, it's on. It's not on yet. Okay, it's on. Good. So the studies I did, I asked people to think in terms of a bunch of primitive tasks and try and teach another person how to do that task that way, and they couldn't do it. They couldn't keep track of all these primitive terms, these primitive actions in their heads, and do anything else that they had to do as part of teaching. So it turned out that was a failure both from the robotics side and from the part of the human side. Okay. The one useful idea we had, and I'm not sure how many of you know about, since you're not AI people, was the notion of hierarchical task networks. Our roboticist friends didn't know about that. They don't kind of learn that sort of AI. But let me show you what I mean by this. So here's the task that eventually our robot learned, and it's doing tire rotation, which has all these subtasks. You'll see things like you have to unscrew the screw and you put the screw down. And that reoccurs a whole bunch of times. And the point of this was, once you teach that once, later on when you're doing some other part of the teaching, you don't have to go all the way down to those primitive tasks again and teach it over again. And that's really important because in this entire teaching, there are 64 primitive actions. And if you have to teach each one of them individually, it takes forever, and people get really bored doing that sort of thing. Okay. So this is the examples of where once you've taught how to unscrew the stud, you can use it again elsewhere in the task, and that makes it much simpler. So that's something that our robot actually was able to do, was be programmed to be able to develop hierarchical task networks. It didn't have that one to start. That's what it learned, but it started with that. Okay, with a lot of work, and this part of the project I was not involved in, these three people and their students managed to teach the robot how to rotate tires. There's a reference, and I'm going to show you, if I can get the cursor in the right place. Yeah, I'm going to show you how they did that.
We have developed a unique new approach for robot learning from demonstration, in which we learn the task of hierarchy and primitives at the same time. We call this SLAP, for simultaneous learning of hierarchy and primitives. Notice how learning task hierarchy via dialogue, learning task primitives via narrated motion capture, and autonomous execution of learned tasks are interleaved in the following human-robot interaction.
Start teaching.
What do you want to call this new task?
Rotate tire.
Okay.
Pick up tire from the floor. Hang tire on laptop.
Should I run pickup tire and hand tire into a new task?
Yes.
What do you want to call this new task?
Mount tire.
Okay.
Pick up nut from table. Screw nut on laptop step 1.
Should I run pickup nut and screw nut into a new task?
Yes.
What do you want to call this new task?
Add nut.
Are you going to repeat that nut on the other studs of the left nut?
Yes.
Okay.
Add nut.
What do you want to call executing that nut on all three studs?
Add 3 nuts.
Okay.
Oops. Oops. Uh-oh. Wonderful.
Please add 3 nuts to the right hub.
Start at 3 nuts. Start at nut. Pick up nut.
Unhang tire for right hub. Place tire on board.
Should I unhand tire and place tire?
In order to learn the task hierarchy, the robot tries to group actions that use the same object.
Should I run pickup tire and hand tire into a new task?
The robot also tries to group actions that are repeated on multiple objects of the same type.
Are you going to repeat that nut on the other studs of the left nut?
Simultaneously, the task primitives are learned in 2 steps. First, motion capture data correlated with human narration is analyzed using motif-based pattern recognition to extract instances of primitive actions. Then, each primitive's constraints are learned by identifying free and constrained regions in the motion data. The resulting task space region representation is used to plan the robot's execution of the primitive.
Okay. So that's how how this happened. And the question is, what kind of challenges lie ahead? So the first thing I want to point out is there were a bunch of unsolved problems that went on in this robot teaching that you might not have picked up on. First of all, vision. There was no attempt to really do vision here. The teacher wore data gloves, a thing on their head, and so that was a way to avoid all the vision problems. The nuts, you may have seen somebody run in and stick a little nut. All the nuts were in a very specific place, so the robot didn't have to look around the room and try and figure all that out. Okay. Robot errors. The robot couldn't make errors. If a nut fell on the floor, it was hosed. It wouldn't be able to figure out what was going on there. Okay. Spoken dialogue. There actually is a dialogue going on here. We actually used an underlying set of dialogue tools that are based on the shared plans notions. But the teacher language was very constrained. You may have noticed the person said sort of very, pick up this and do that. That's partly because the speech system was a bit challenged. But it's also that there was an attempt to really make the dialogue very free-flowing. So it's a very simple dialogue in that respect. And here's the other really important thing, is the robot doesn't know much about the world. It knows about screws. It knew what the tire was. It had some very simple notions you may or may not have seen. It looks at the person when the person's talking to it, looks at the mock-up car when it's doing something, and that's about all it knows, and all of its knowledge was built in. It wasn't trying to learn anything but specifically about how to do the tire problem. Okay. So I asked the question, well, how do people teach other people tasks? And here it's like Back to the Future, because, of course, Barbara has just finished telling us about, way back in 1974, about teaching how to put together or take apart an air compressor via dialogue. And the question is, so why did you do this over again? And the answer was, well, now the teacher and learner actually have to talk to each other, and they're co-present. And that raises a whole interesting set of questions, which I explicitly wanted to look at, because when you talk about a robot, that's the sort of circumstance you're actually in. Okay. So how do people teach tasks? Well, the task I set was to do car engine maintenance tasks, okay? We made a mock-up of a car engine. You might get a kick out of this. It has a chassis in the middle. The blue bottle is the windshield wiper fluid. The orange bottle in the bottom is radiator fluid. There's a little thing sticking up. That's the oil for the dipstick. And at the very back is the air filter, and they had to take apart the air filter and put another one on. So that's the kinds of tasks there were. We had two people, one a teacher who knew how to do these things, and one a student who did not. There's an instance of a teacher and a student working with the mock thing. We did 8 different pairs of partners and 3 different conditions. The first group had no restrictions of what they could say. They could do anything. The second group were the groups where I asked people to try and use names of primitive actions, which they had a lot of trouble with. And the third group had a confederate, which was me. I dressed up a little bit like a robot and tried to act like a robot because I had discovered from the other things that it was hard, that the robot would have a hard time understanding certain aspects of what was going on. So I figured it would be interesting to see if I asked questions that would be useful heuristics that a robot would actually use and see what happened, okay? So, and we videotaped everything, of course. Okay, so here's a sample interaction, and now I'm going to have to stop things for a second because my computer is not getting the same thing to look at it. You are. Ah, good. Now, where's there we go.
We'll start with probably the most basic. Windshield wiper fluid. Blue, and you'll see it in the blue, it's not in a, so obviously that's recreated, but that's your windshield wiper fluid.
And that line.
Yeah, so you can tell that it's low because it needs to be up to the fill line. So I'll go ahead and, she wants you to go ahead and do it, and then you can do it. So yeah, and then you can use this little dandy phone. And you just want to make sure you obviously don't go over the line. Okay.
Okay. So there are some interesting things to be noticed about this. First of all, teaching and learning are collaborations. They are collaborating in both subtle ways, like when one other person points at things. They're also collaborating in much bigger ways. The language, as you would have seen, is very informal. In fact, since you're not all native speakers of English, I wouldn't be surprised if some of that language was difficult for you to follow. And then there are inescapable knowledge issues. They talk a lot in these dialogues about preconditions, postconditions, effects of the various things they're teaching, and they do that a lot. And so I was curious about the problem of what knowledge could be built in and what could the robot be taught. And so to get at some of that, I'm going to turn to some of the language that was actually used. And so for the next little while, we can all just be computational linguists, okay? The first kind of thing people did a lot of was they talked about actions. And their talk about actions is actually very simple. It's we do, this action, you do this action, do this action, those kinds of very simple ways to talk about actions. It makes life really easy. You can imagine using case frame semantics, we're all done, okay? Now we get to things that are not so pretty, conditionals. There's all this talk about conditionals, which is no surprise if the oil's below this line, until the screw fits. These are all essentially, you would think of them as qualifiers on what's going on. And then there are purposives. There are lots of purposives that go on. And these are things like, just leave it so it holds it. We put it back here so we don't lose it. I mean, all these interesting kinds of language behaviors. In the case of the conditionals, the syntactic behavior isn't that bad. Even in the purposives, the syntactic behavior is not very terrible. But the place where it gets interesting is sentence semantics. Not the action stuff, but when we start to look at conditionals, some of them, like the oil is below this line, at least the semantics of that is not too bad because it's about spatial relations. But things like we need to put oil in, or it's fully screwed, there isn't enough liquid in there. I think the sentence semantics issues of these are quite complicated, and this is where computational linguists have a lot to offer, okay? Same thing when we get to purposives. These are all pretty interesting semantic questions, and they are the sorts of things that are nice challenges for the computational community. If we turn to intended meaning, again, the actions. Okay, this is what you're supposed to do. That's no too complicated. But when we get to conditionals, a bunch of these are either preconditions on some kind of action. They're expressing postconditions. My favorite one is the one I didn't label, and it's the reason I like this is you get a chance to see how hideous the language is. What they're really saying is if it's not up until here and there's a pointing going on. But you get all this kind of odd language that's trying to figure out what the person wants to say before they get to the right thing, okay? In the case of purposives, we have one thing that's clearly an effect. We have conditional effects. There are things like warnings. We put it back here so we don't lose it. That's kind of warning about don't do this, etc. So there's a bunch of interesting problems in terms, again, of the language behavior. Okay. So when we ask the question about knowledge to build in, well, we surely want to build in good syntax, semantics, and intended meaning, interpretation. We're not going to leave people to try and teach that sort of stuff. Obviously, we want to build into whatever domains we're ever going to worry about, things like color, spatial relations, shapes, time, because these occur across lots and lots of circumstances where you might want to teach a robot. And maybe you'd want to build in some kind of conventions about how to identify objects, to make, this is a screw or some variations of that, something that kind of language and that conventions for doing that is a regular thing, and presumably other things. But what I want to claim is you can't build in all the knowledge. Well, maybe you can, but I think if you were to do that, you're going to have to wait a lot of years before you can build a robot that could be instructed in lots of different domains without knowing everything ahead of time. So let me give you an example of this. Some of the conditionals here, like the oil is below the line, has to do with spatial relationships or putting something in something else. But the three in green in the middle definitely have to do with the domain about screwing things onto other things, which is what you have to do with a nail filter. You have to take off the screw, take apart the air filter and then put it back together. Things like not enough liquid in here. Well, enough is a kind of comparative, and what counts as enough is very domain specific, and the sort of thing you can imagine a person saying this and the robot saying, I don't know what enough liquid means here, will you show me? And therein you'd want to be able to teach that kind of thing. But of course that presumes we've done our work as computational linguists so that this whole kind of behavior could happen. Okay. Similarly, for purposives, these are really great, I think. So it holds together because the funnel is too big. Well, big is another wonderful comparative. It's going to depend upon the domain, not losing things, etc. So what I'm getting to here is there are a number of exciting challenges. The informal and rather incomplete language is still a very big problem, not only in computational linguistics, but in speech. Sentence and semantics and intended meaning are not well understood, but it's a wonderful area to start look at these kinds of problems. And it might not be that all the knowledge has to be in the box when you get the robot, that there might be ways to teach it. And I think there's a very interesting challenge in asking the question, how are people going to teach relationships, states, properties, and objects about a specific domain? So we have work as computational linguists. We could be offering the community of people who are really thinking about how to get robots to do interesting things in the world a lot of expertise that they don't have. I generally go to the major international conference called Human-Robot Interaction. There are almost no linguists who go to this, no computational linguists. I'm kind of a singularity at this event. And I think it would be an area in which there is a great deal of interesting work that could be done. Now, I'm going to take 2 more minutes, and I'm going to talk about 2 other challenges, just briefly. This one is the challenge of deixis, of gestures, especially deixis. I'm not going to go through the video here, but the video you saw at the beginning, there's actually a lot of pointing behavior that was going on there. The last time I was here, I talked about some work we did on getting the robot to produce deixis, but understanding deixis that a human produces is very tricky. It's not just pointing like this. There's these kinds of gestures. There's holding things up. Those are all deictic gestures. And then there's a lot of other kinds of gestures that the human-robot interaction community is very interested in and has begun to work on. Things that have to do with where you position yourself relative to other people, how you look at them, etc. And then I want to raise one last problem. Not only can robots make mistakes, but believe it or not, teachers make mistakes. So here I am, dressed up like a robot, just watching while this person is explaining how to put the oil filter, how to deal with the air compressor, or not the air compressor, the air filter, and how to put a new air filter in. And you'll see he's holding the dirty air filter in his left hand, and he's screwing a screw back down to get the air filter to be back together. But he forgot to put the lid on the air filter before he screwed down the screw. And if you listen carefully, you'll hear him say, "Oh, that is a mistake," and then you'll see what he does. And again, I have to restart this thing in a particular way because my computer isn't happy. Come on. Okay, here we go.
And then we put the screw back on to make sure that it does not move. To put it on, we just put it on the screw and rotate it clockwise. Keep rotating it until it's fit. So this one does not move. Now we put this away, the old filter. Oh, we have to put this. I missed the cover. That is a mistake. We have to put the cover back on the air filter. To make sure, this is really important, we have to make sure we put the cover before we put the screw.
Okay, so this is not the first problem I would tell a PhD student to work on, but it's not a problem we can ignore. And it's challenging because mistakes don't happen very often. You'd like to have a big database collected by all your friends and yourself and everybody else you know with lots of these kinds of examples so we can understand what that behavior is. All right. So to sum up, that's what he actually said. I'm going to skip that. Teaching a robot offers us a bunch of challenges. The use of everyday language, issues about semantics, sentence semantics, maybe deeper semantics as part of the way you want to think about it, intended meaning, teaching domain-specific knowledge and how that might go about and what the language behavior actually is for that, producing and interpreting deixis, among other kinds of gestures, and dealing with errors both on the part of the robot and the part of the teacher. And it might even turn out that teachers want to teach robots what to do when they make errors. So there's lots of wonderful challenges here. It's not chatbots, thank God. And I hope you will all kind of tune your ears up to look and see what the robotics community is doing, because there's a lot going on, and it could be a lot of fun to be thinking about some problems in association with them. So, questions?
Thank you very much. There were can you put on the last but one slide?
Oh, sure.
With the summary, because actually these are the challenges which are on your slide. I mean,
right.
The challenges that have to be solved. So, do you have some questions or hints how to answer the challenges?
Oh, yeah, right. I don't even have an answer. I have some ideas.
I will be back to one of your, actually to my question, to your talk. You said that, and I think it's completely true, that there are specificities of the different domains.
Yes.
And on the other hand, or contrary to that, Barbara said that one challenge is to have something like open space or open domains. Is this a difference between the world of robots and the world of the dialogue analysis, or is there something?
So what I think about this is that these kinds of teaching tasks are both open and not so open. So once you specify a particular domain for the robot to learn something, and whether it's car maintenance or setting the dining room, the dinner table, you've reduced some of the difficulty of the world because there's only a certain number of things to talk about, and there's a structure to what it is that's going to happen. Okay, and and it has to do with the structure of what those tasks are. I mean, this is not anything new, not anything surprising, but it is a little more closed in the sense that you're not going to, if you're talking about setting the table, you're not going to talk about, I don't know, physics problems or teaching children how to structure blocks or whatever. So you get kind of what I would think of as a quasi-open domain. The challenge, of course, is that when you think about several different domains, how do you plan for the robot to have capabilities that could be brought to bear in a bunch of them? So I think that means, among other things, getting lots of examples, collecting data for different domains, spending some time asking the questions, what's similar, what's different about the way people go about them, et cetera, et cetera. And I've just given a kind of limited insight into this, having looked at the problem of just car maintenance tasks. very small kind of step in that direction.
So
No, it will be.
it's recorded. Yeah. That's an interesting answer and somewhat different from how I might conceive of it. So one thing is she's talking about teaching the robot the domains, and I think when you're teaching, you have you can define a sort of closed world. It's just like when you give a conversational agent a template for a certain domain. So the question is going to be, which is sort of what I think you're getting at, Candy, that if the robot then goes off to interact with people, you're going to have the same open domain challenge because there's no guarantee that the person the robot interacts with is going to stick within the domain you've taught the robot. But if your goal is to teach the robot how to do something and then the robot's just interacting with an artificial world, or with a physical world, and the physical world obeys what you presumed and what you taught it, then you have this maybe quasi-open. I mean, the more it's different from what you've taught the robot, the more challenge you're going to get. So I think there's really a question of what's the domain. Yeah, what's the domain, and what, not just the domain, but what's the task that you're doing, and how much will the robot experience the task slightly differently from what you taught it to do. And I think they're the challenges. So one thing you might say is, let's use machine learning. The area of AI in which the least has been done with machine learning is planning.
So I have a comment about this a little bit. We do use machine learning in the work that you saw the video for. It's a very specific kind of machine learning to figure out where the primitives actually occur, both in what the people are saying and what the robot's seeing that happens in the interaction. It's not the kind of machine learning that takes a gazillion tons of data. I mean, there's a general term in the robotics community about one-shot learning. Sometimes one-shot learning means something else, but it's this very brief set of interactions. It's not let's do this thing 10,000 times kind of stuff. But it's definitely, that the machine learning stuff is definitely there. It's not there, of course, in the hierarchical stuff because, the robot asks various things, the person shows them once, and then you're supposed to be able to do it. And so far as that kind of task worked, it does actually do it. So I'm curious, do you all have a reaction to things like what it takes to do the kind of data collection and analysis that I'm kind of alluding to? I'm curious to know what your sense of that is, for example. You must all have some experience collecting data. Yeah.
Well, maybe I should explain why this issue of domain-specific and open general domain is just at the top of my stack, because I have reviewed some submissions for interspeech in the dialogue domain.
Yeah.
And it seemed to me that whenever the authors wanted to make a kind of open space, then they were restricted to extremely simple structures.
Yeah.
So it seemed to me that maybe that's why I asked whether it's a different task, because it seemed to me that if the task allows for a simple structure, then one can speak about or use it for open domain. When you want to have something very specific, you must, or more complex structures, then probably this complexity depends on the domain more than on the when it is open. So it was just because I had this.
And there's a response behind you, too.
Well, it's actually not a response to your question, but it's a few thoughts thinking of how the robot actually acquires the knowledge to do something. It goes through the language, what the teacher says, through the visuals, what the robot or what the teacher does. And I'm wondering if there is any thought on whether or not the robot has to infer some details. For example, if I show the robot how to screw a screw with a screwdriver, there is this little detail that the screwdriver has to be aligned with the slot on the screw, otherwise it doesn't work. And my question would be, is there a mechanism for the robot to infer that and to actually make sure that it has inferred it correctly? For example, is the robot capable of, let's say, well, I'm afraid to use the word think, or realize that, okay, if the screw doesn't move as it did when the teacher did it, is there something wrong? So any comment on that?
So these are really open questions. Trying to get robots to do tasks of even the complexity of what I showed in that video is a kind of big step forward. I think the example you raise is a really good one because your human natural inclination is, okay, you put the screwdriver in the slot and you just do this, and that's all you have to say about the matter. We could very well imagine that what happens is that isn't enough information. In part, let's assume the vision stuff worked really well, but that's not enough information for the robot to be able to reproduce that activity. And in which case, you'd like a robot to be able to give you some information about what's wrong, or this is not something I really thought about. The robot tries and fails, and then the person goes, oh dear, I'm going to have to break it down more and more. So there are really interesting questions, I think, about how that happens. And if you think about then the language question, the language issues that come up with that, that's our challenge to deal with. Yeah, Barbara.
So I also think this is an interesting question, and it leads me to a slightly different but related question for Kenny. So one of the things people are thinking about, in particular with traffic and automobiles, is that if we really want a future with autonomous automobiles, we need to think about how to redesign the roads. And so what your question made me think is, well, why should a robot have to use a screwdriver? Maybe we should redesign what the task is. If you go back to you want to assign to an agent something it's capable of doing. Maybe robots aren't capable of screwing screws like we do, but they can do something else, and you can have a different kind of fastener. And so that just trying to get a robot to mimic what people do may not be the way you want to get a task accomplished. So the question for you is, do you have insight, as you've tried to do this, insight about the kinds of things you would want to change? Like if a robot isn't a human car mechanic, so what might you want to change so that the robot could do it easily, so you actually would never run into can you get the screwdriver into the screw right problem?
So in general, the robotics community is not happy with those kinds of questions. And the reason is that, for example, putting robots now, the next generation of putting robots in factories is you want to just put the robot in the factory next to somebody, show it how to do something, and it does it just like its human counterparts and eventually kind of takes over some spot in the chain. And there's also this notion that, so one of my robotics colleagues always said, maybe we just need to redesign the world so that the robot has an environment that's more friendly to it. And whenever he said this with a bunch of other roboticists, they all went, oh no, that's never going to work, because how are they going to work in our homes and blah, 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 blah. So I think there's a really interesting question there about how much we can change the environment in which the robot works in when it's an environment that we work in too. And cars are a particularly interesting and curious case because the assumption is they're going to drive down the streets we drive down, et cetera, but there's all these assumptions about how they're going to talk to each other, but they're not going to talk to the human drivers. I mean, I think there's a lot of details to be worked out there. So,
I just want to note that in the history of automation, I've learned recently that mass manufacturing only finally worked with respect to making things less expensive when they redesigned the factory.
yes, right.
So, of course, people are going to resist redesigning, but you could design smarter intersections that would not still let people drive and would make it easier for autonomous vehicles. So I think it's a pretty subtle question about how to do this.
It is a subtle. It's a very
designing right, but I'm a bit skeptical of people who say we can never do that and the machine has to do it just like us.
Right. But certainly there is this tension in the robotics community about exactly that point. And I don't get to, since I'm not really a roboticist, I don't get to, in some sense have a vote. I'm just aware of the arguments that go on. So.
Well, back to your question. When you, at the beginning, you spoke about this, I don't know whether you called it primitive actions.
Primitive actions.
And I would take these, what you have referred to, as something like conditions for the primitive actions.
Yes.
That primitive action can be done if, and now these conditions, if they are fulfilled, okay. If they are not fulfilled, then...
That's the whole precondition
Yes.
and post-condition stuff that people and I have talked about for a long time, and which clearly comes up in the language that people use when they're teaching tasks. So the demo you saw of the robot actually doing that, there was none of that kind of language at all. It was a much simpler problem. But I think the real problem is definitely going to have that kind of behavior, and that's why the linguistic issues, I think, are important. So,
Change the topic back to a question Ava asked me and related to producing and interpreting deixis. And I think the examples you gave are the simplest deixis. And when Ava talked about situational references, it seems to me you have, it's not a play, but you have this writ large in this environment.
yes, you absolutely do. Even with the actual example of the robot learning something, almost all the references were extensional. The screws, the nuts, the tire, it's all extensional language. Nobody did any deixis at all, and but I've collected many other kinds of tasks. For example, people teaching someone else how to make food, simple kinds of food, and there's a ton of deictic behavior in all of that. It's where you get things not only like pointing, but you get this thing and that. You get a whole lot of different uses of the hand to explore deictic possibilities. And in fact, one of the examples I didn't show you, the young woman she points at one of the objects without even opening her mouth. So we get deixis without language. So there's a lot of interesting challenge there, I think.
So, no hands up?
Actually, one of your slide you have shown, the teacher is instructing the it's like a teacher instruct the robot to learn, right? So, in general, if you look into in general sense, the same thing can be done by the way of teaching will be different from different people. Suppose, for example, how I teach the student, or maybe one teacher teach the same topic, maybe it will be different from other teacher. So maybe the person who is teaching the robot, if another person will come, maybe his teaching style will be little bit different, right?
Oh, so that's a very interesting question as well.
So
people have different teaching styles, essentially?
Yes. So my question is that, is there how you define one standard to teach the robot? Because maybe if like teachers, teaching style can be different or the instruction set may be different. So how we can define one standard, or we can say this is the correct procedure to teach the robot?
Oh, so that's okay. So you're asking what's the real procedure that I want to teach the robot? Okay, so notice in the original scenario, there was no claim that there was a specific way to do something. There was simply The robot's there, and I want to use it for something, and I have to teach it how to do something. Up for grabs whether somebody else would do it differently, but if people do it differently, of course, this robot must be able to do that sort of thing, or it's going to fail miserably when you take it out of the box in certain kinds of situations. We don't know. Are there going to be several different teaching styles for certain kinds of tasks? Now, we're mostly talking about physical tasks, things that involve very specific things about the physical world. If we were teaching mathematics, we're not up to that, I don't think, at this point in time. That would be a very different set of concerns and conditions. But I think you're right, there is a question about whether there's a right way to teach it, whether there are different styles. I don't know the answer to that. Yeah. So, thank you. Yeah.
Thank you.
Well, if there are no hands in the audience, then I would like to thank you for your talk. Well, we probably will not build a robot in the nearest future, but still we know what the challenges are. Thank you, and thank Barbara for coming again. And well, as I said, we hope to see you here
Goodbye,
sooner.
Sure, good.
Yeah. So thank you very much.